Yeah. So it's my great pleasure to introduce today's speaker, Balaji. Balaji is a distinguished fellow at the Schmidt Futures, where he's leading the new programs in climate and computational sciences. He's also, and I'm going to get this right, Make Our Planet Great Again Fellow at Sorbonne University in Paris. In fact, he was one of the first recipients of this fellowship, which, as you know, is a high-profile initiative started by President Macron in 2017 to host and support leading US climate scientists in France. Until recently, he was the head of the climate modeling division at the Geophysical Fluid Dynamics, or GFDL, lab in Princeton. Actually, at the GFDL is really the birthplace of climate models. This is where Suki Manabe, who got the Nobel Prize in Physics in 2021, his colleagues developed the first generations of climate models in the 50s and 60s. And the next generations of the GFDL leaders, including Balaji, really evolved these models to become the very powerful tools that they are today. But as amazing as the climate models are, they still have problems in giving us very reliable answers about important questions, for example, how the extreme weather events will look in the future. So as a result of that, there are growing international efforts in improving the climate models, and AI, computation, and data, they have been playing increasingly important roles in this area. And Schmidt Futures has been one of the major supporters of these efforts around the world. And Balaji has played a key role from the beginning in formulating their vision in this area. I should add that I've been reading Balaji's papers for over a decade, and I've been interacting with him for the past few years. And one thing I found always fascinating about him, and you already know this if you met with him today, is that you can talk to him about the most detailed technical issues, something about physics or about computing, something that could be even like a line in the Fortran code, or if you are from a new generation and don't know what it is, in the Julia code. Or it could be really about the big picture of where the climate modeling and climate science is going in the next few decades. And he has basically heavily published in these areas, and that's why we thought he would be a perfect speaker, first speaker for this series. So we are very happy that he's here today, and he's going to tell us about his thoughts and visions for the future of climate computing. So join me in welcoming Balaji to us.
Thank you. I'm wearing a lapel mic. I hope the two mics is not a problem, and I hope there's no feedback. And thank you, Pedram, for this very kind introduction. So I should begin by saying that I did meet the late Ken Kennedy a couple of times. There's been, I spent 25 years in Princeton before moving to Schmidt Futures, and during those 25 years, there's been at least two major inflection points in the way computing is used in climate science. So when in 1996 is when I joined Princeton. Around that time is when we were making the transition from towards parallel computing. And parallel computing was a very fascinating field to get into at the time. I really enjoyed that phase of my career very much. When we were taking the climate models we inherited from Manabe and others, I'll be speaking about Manabe's work a little bit, and converted them to the new kind of computers that were coming around at the turn of this century, at the beginning of this century. And parallel computing, of course, brings all very fascinating computing issues, like the same word in memory is being accessed by multiple processors, who some of them might be writing to it, some of them might be reading from it. And you have to keep these, to get the correct computation, you have to keep these things done in the correct order. And Ken Kennedy was one of the pioneers of doing this, getting compilers that understood parallel computing very well. So I can't claim I knew him well, but I met him a couple of times at supercomputing conferences. But today, and he also, even back then, he had started talking a little bit about machine learning. So that comes us to the second phase. So the kind of work that Pedram is alluding to, and that he himself is one of the new generation of scientists who's pioneering this kind of work. It's the second transition that has taken place in climate computing in my lifetime, in my career, which is the transition where machine learning is actually changing the way climate modeling is done. And that's what this talk is going to be about. And I'll start by talking about what a GCM is, the general circulation model that we have been using since the time of Manabe, and how it has evolved until today. And some people have said that maybe that structure needs to change. So there's some problems with it. I'll talk about what the problems are. I'll talk about what has happened to computing technology, which is pushing us towards this new way of doing computations, which is largely based on machine learning and dense linear algebra. We'll talk about emulation, when I talk about climbing down the ladder, it's a reference to something Jules Charney, who's one of the pioneers of, again, even before Manabe, one of the pioneers of the field. He spoke about models, and as computers got bigger, you build more and more complex, more and more detailed models, and he called it climbing the ladder. And I argue that emulation is a way of climbing down the ladder, starting from very complex data sets or complex simulations, and then learning what is essentially the fundamental equations underneath that, or the manifolds underneath that, and try to extract that, and I call that climbing down the ladder. And this transition, I'll explain what GCMs will continue to do in the future. So let's start with this model, which is one of the ones cited in the Manabe Nobel Prize. So it's a simple 1D model in response to what happens to the planet in response to CO2 doubling. So if you look at it, it's a vertical profile of temperature, and it's showing, so there's two processes that are happening. One is that the atmosphere cools to space, so radiatively it loses heat to space. So that's a cooling effect. What that does is that it heats at the surface and cools aloft, so there is a gradient there. And that creates a gradient of temperature, so that's a stratification. So it makes the temperature profile, look something like this. Once the temperature gets highly stratified, that is very warm below and very cool above, the atmosphere will start convecting. And it'll redistribute and unstratify the atmosphere or mix the atmosphere. So what they did in this model is, in a simple 1D model, this shows that these two processes, radiation and convection, eventually come into equilibrium. For a certain quantity of relative humidity, you will get a certain profile of temperature, and that's what this profile looks like. And what they showed here was that the way you do it is by you start with any kind of distribution you like, and you start the two processes, and you'll eventually equilibrate into this final state. So there's an attractor in the system, and you can find it. But what they showed is that if you add CO2 to the atmosphere, that changes the radiative balance, because CO2 is a radiatively active gas. And what that does is that it changes the distribution. And if you go down and look at what it's doing right around here, which is zoomed in, you'll see that the surface temperature warms. So this is the first result that showed that if you keep adding CO2 to the atmosphere, it's going to warm. Okay, so this is just vertical redistribution. What do you do next? You start building these kinds of models, which is Manabe and Bryan, another landmark paper, where they put in land and an ocean, because some of the heat that you distribute is going to go to the ocean. And you can go further, and then you can start doing now, you're not just distributing heat vertically, but you're also distributing it horizontally. If you look at the way the Earth is situated in space, most of the incoming radiation is close to in the tropics, and is losing heat near the poles. So there is some movement of energy, not just vertically with convection, but also horizontally in order to transport the incoming heat towards the poles. And if you solve this in 3D, you will get something like this. So the dots are some observations. And if you have one profile of temperature as a function of latitude, and you double the CO2, and you let it run to equilibrium, you'll get a different profile of temperature, which is warmer. So even if you include 3D, then you're still showing that the equilibrium response to doubling CO2 is a warming of the entire planet. And it doesn't matter what your initial condition is. So they're starting from two different initial conditions, one which is warmer than the present day temperature, one which is cooler than the present day temperature. And you see that they both equilibrate to the same final state. And in this case, it's taking about, in this highly, somewhat simplified model, it's taking about 2 years, 700 days or so, in order to reach the equilibrium state. If you run a model today, which has the carbon cycle, it has a lot of complex physics, it has a three-dimensional ocean, which is also distributing heat into the deep ocean. All these processes are very slow. So the equilibration times in modern GCMs can be measured in thousands of years. That's an important thing to keep in mind, because you have to remember these models that we have to run in order to study the carbon cycle, the warming of the Earth, all these things. You need models that can run in simulated time for thousands of years. So what does a GCM look like, a 3D GCM? This is what it looks like. It's a discretization of the sphere, and the discretization in the vertical. So you have these columns, and the columns can talk to each other because there is flow going, horizontal flow going. And we have this peculiar terminology where the resolved scale we call the dynamics, and everything that's unresolved, which you're representing inside the grid cells, we call physics. And in the physics, you can have clouds, you can have exchanges with the ocean, you have all kinds of stuff. And as computers get bigger, you can keep increasing the resolution. You can also add detail. You can add both complexity, the number of processes you represent inside this box, you can add to that, and you can also add resolution. So there are both these things you can do. And so the computing is consumed along both these axes, so it limits the amount of resolution you can keep adding to the model. So one of the things we do have to model is clouds. So clouds are very complex. If you look at this, is just a random satellite picture. You have big clouds, which are anvils of cumulus clouds that can be distributed over thousands of kilometers. You can have very small clouds that are sizes which are measured in kilometers or smaller. And the way you do that is you make some kind of assumptions that you have an ensemble of clouds of different sizes, and they're in some kind of close to equilibrium. They're trying to equilibrate in the same radiative convective process. They're trying to redistribute heat until they come to a kind of equilibrium state. And you can come up with various theories of how this happened. How do you destabilize against a large-scale environment? And you come up with some sort of, so you have the large-scale environment, which is what you resolve. And you say clouds are going to redistribute heat, moisture, momentum, all these quantities. A population of clouds is going to do that, and you write a theory for that. And that's called the parametrization. Now, the parametrization of convection has been going on now for 50 years, since the original Manabe model, which I showed you, was 1967. And the progress, we can certainly say, has been slow. So you can ask the question, can this thing, the redistribution of heat, moisture, momentum by clouds, can you actually write it as a function of the grid scale? Or maybe it's too complex that you cannot do that you actually have to do resolution. You have to actually resolve all the processes. So many people are asking the question, maybe clouds are not parameterizable at all. And what are the reasons for it? There are many kinds of clouds. So within the same column, you can have different kinds of clouds. Clouds tend to organize themselves. You have what's called organized convection. So you can have them in the form of lines, which are called squall lines. These days, many people talk about derecho systems. You can have cyclones. You can have mesoscale convective systems. Cyclones are more rotating forms. So from the point of view of a column, they're non-local. You cannot just describe them with just the information in the column. You need data from neighboring columns. There's lots of small-scale dynamics. There are when the air descends, when there's a downdraft from the convection, it creates a cold pool, and the cold pool creates convergence, so you can make a new cloud come up. There's microphysics, which is actually how cloud particles, cloud droplets interact with each other. If they meet each other, they can coalesce and make a bigger droplet. If a water particle meets an ice particle, it can freeze. All these things happen. They're happening at micron scales. You're certainly not going to simulate all these collisions and all these things. That's happening at too small scale. So what happens is that when you try to parameterize these things, you start with a simple scheme, a simple theory, and then as you start comparing it with the data, the schemes get more and more complex, which I call Ptolemaic, which is what happened to Ptolemy when they tried to build a geocentric system and tried to explain the movement of the planets. As the more and more data they got, the harder and harder it was to build a geocentric model. So that's what happens, and there are systematic biases. So for all these reasons, people say, this is why I'm showing it as the column is broken. So the column does not work anymore, so we have to throw it away and do something different. So what can you do? You can just shrink the size of the column, so you can go to very, very high resolutions. Now you have to go to get to deep convection, you have to get to maybe kilometer scale model, which people have been doing. This is actually the reason I picked this picture is this from Tao's work, dates back to the 1980s. So these kinds of models on a very small domain, obviously you cannot do this on global scale, have been going on for some decades. If you go to the boundary layer alone, which is about in the planetary boundary layer, the depth is measured around kilometers. You can have clouds which are just confined to the boundary layer. These are not the deep clouds that create thunderstorms, but these are just small clouds in the boundary layer. To get the dynamics of this, you have to actually shrink the resolution even further down to meters. Now, this is just turbulent, moist convection, but it's turbulent. So you can also do this you can do these things. These are called LES models or large eddy simulation models, and these typically run with resolutions of meters. And the whole domain is measured as a few kilometers. So super parameterization is another idea that you can do, which what you do is that you start with your low resolution model, which now the resolution is measured in hundreds of kilometers. You're not resolving the convection. You embed one of these CRMs, these cloud resolving models, inside each column. So you can understand that this is also, in this case, you're not solving the whole 3D flow. It's too complex, too computationally intensive. So you're solving a 2D model. Only 2D models are computationally feasible. And using this, you can start doing this, and this already began to interest the machine learning audience, because now you have a clear thing. You have something called the CRM, which is computing these things, but it's using lots of data. It's computationally very intensive. Can you learn what it's doing and represent it using a neural network? This is some of the very early work with machine learning looked at these problems. Now, what's the problem here? I mentioned turbulence. Turbulence can be thought of, this is early data from 1985, but it's still very true. So this is the basic problem. So on a sphere, so geophysical turbulence, on very large scales, which here is shown as thousands of kilometers, it looks like a 2D flow on a sphere. And that typically, turbulence theory shows that should typically have a -3 slope. That's what we observe in the atmosphere. Once you get below that and baroclinicity or vertical motions become important, you get to 3D geophysical turbulence on a sphere. And that can be shown to have a -5/3 slope. So this has been known since the very early days of turbulence physics, so the 1920s. And that 3D thing continues down to, you can see down here, if you go down to sub-kilometer scale, down to meters, it's still true. It actually is true down to even centimeter scales, down to what is called the Kolmogorov length scale. So there is actually no place at which this turbulent cascade stops. So whenever you discretize a model spatially, you're just stopping, you're truncating it somewhere. If you're using a 100-kilometer model, you're truncating it here. If you go to a 10-kilometer model, it's here. But whatever you're doing, there is some amount of turbulence that you resolve, and there's some amount that's unresolved. And we have to capture this. So this is what is called the SGS, or subgrid scale physics. And we are now trying to see what we can do with subgrid scale physics. When you go to the ocean, it becomes even more complicated. Here, it's not simply a matter of knowing the Kolmogorov length scale. The length scale you have to resolve, it's called the baroclinic deformation radius. To resolve it with the delta x, with the resolution of your model, this shows on a map of the world what resolution you need to get to. So in the center of the tropics, where the flow is relatively laminar, that the resolution is pretty high. It's around 1 degree, which is about 100 kilometers. But when you go near the poles or near coastlines, because the bathymetry, the depth of the ocean becomes smaller and smaller, this length scale also changes. And then you get down to, in some places, 1/50th of a degree, which is around 2 kilometers. So there's a huge range of scales. And you cannot, if you want to resolve all of it, you have to get down to 2-kilometer resolution, which is computationally quite unfeasible, as I'll show. And this is what really ocean flow looks like. So when we show it, schematically, we say there is something called a thermohaline circulation, which is a south to north flow in the Atlantic. And we say in the middle there is something called the Gulf Stream, which is a west to east flow. But when you really look at it at depth, this is what it is. There's a lot of wiggles and turbulence and eddies and all these things. And they're all quite important. How eddies transport fluid is quite significant. So somehow we need to get these details right. And so if you move this to the global scale, you can get to global CRMs. You can run these today. There's a program called Diamond. But because of the computational challenge, you can't run them for very long. Remember, I mentioned that you need to be able to run thousands of years in order to just equilibrate the climate. These models can run for a few weeks. The first Diamond experiment was a 40-day experiment. So they run for about 6 weeks of simulated time. So nowhere close to running years. And the resolution of the model has been changing over time. So normally you expect, so this is the computing challenge that we tried to solve with parallel computing. So with parallel computing, we were able to take advantage of Moore's law, which said that this is the blue curve that's shown here. Every 18 months or so, you double the amount of transistors you can put on a chip. And then you should get, so this is on a log scale, you can say how much computing power is evolving. But if you look at actual models, you can see that they're not keeping up with Moore's law. The resolution has tapered off, sort of like this. It's become flatter and flatter over time. So starting around 2000, we have not seen much increases in resolution. And at GFTL, from the Manabe-Bryan model to today, the HALE 2019 is the latest model called CM4 that came out of GFTL. There's been a 10x increase in resolution, from 500 kilometers to around 50 kilometers in the horizontal, and from about 9 vertical levels to about 90. So it's been 10 in both X and Y directions. So you can see this taper, and you keep that in mind. So, and the other thing you have to keep in mind is that models are used in various ways, and this is quite important to see as well. It's not just the length of the simulation. We don't know a lot of things about the models, and we don't know a lot of things about what is going on in nature. So one is that the system is chaotic, that's shown here in orange. So starting from, that's called internal variability or just chaos. So based on small changes in initial conditions, you can have different states. So that, but that goes down, that source of uncertainty goes down over time. The external forcings are things like the CO2 that's emitted by human activity. And we don't know how that's going to change in the future over 100 years. We don't know how policies will change. We don't know how technology will change. So there's a huge uncertainty coming from that. And then there's the uncertainty which we call structural or epistemic uncertainty, which is what we don't actually understand fully about the climate, like the clouds example I showed. So in order to sample all these uncertainties, we have to do a lot of counterfactual things. And what does counterfactual mean? So think of it again, we are going to talk a lot about machine learning. Machine learning says you just train on the data that you have. Counterfactuals means you need to train on stuff that not only has not been observed, will never be observed. So we need to sample a lot of states for which there is no observational data, but you need that in order to make the kind of studies that we need to do. I'll show some examples of that. So a climate model, this is not weather now, a climate model, you need to sample all this uncertainty. You must be able to do hundreds of simulations, and the length of this, as you can see, is around hundreds of years. So think of that as a kind of limiting technological limit. You need to be able to run hundreds of simulations, hundreds of years long. That's what you need to do with a climate model. And you have to do it on available computing. And the other reason why you have to worry, again, overfitting is another thing the machine learning community is quite familiar with. And you only have about 60 years of good climate data, which is the satellite era. Sputnik is 1957. And we have some problems with the models that we understand. So there's one technique is that you take your observations and the model tries to go in a certain direction. You use observations to force it back to stay close to the observations. That process is called data assimilation. And you produce data sets which are called reanalysis data sets. And in this study, what they show is that there is a circulation which is called the Hadley cell. And the Hadley cell strength, which is the strength of the tropical circulation, broadly speaking, a lot of models are showing that that's declining over time with global warming. As the climate warms, that circulation is going to go down. On the other hand, these reanalysis data sets are showing that it's going up. And the reason is that the reanalysis data, the model which is trying to be physically consistent is trying to go in a certain direction. So observations are trying to force it back to what is actually observed. And that what is called the increment, which is the forcing towards the observations, is not necessarily physical. It is just an extra term that's added to make it stay close to observations. That actually violates certain physical laws. And so the conclusion of this theory is that this green data, which we think of as observations, is actually probably not correct physically, and the blue data is actually correct. So you have to be very careful if you're using actual data to train with, that you know whether it's good or not. Let me switch a little bit now and talk about computing technology. So you remember the curve from a few slides back, this one. You saw that even though Moore's law is going on a logarithmic trajectory, the model resolution didn't actually go. And here's one reason that might be why. So this is showing how computing technology has actually evolved over the last many decades, again on a logarithmic scale. So the orange curve on top is the Moore's law. So it is showing, again, logarithmic doubling every 18 months or so. The number of transistors on the chip keeps doubling. It's going faster and faster. The green curve is an important one to look at. It's what's called the frequency. It's the amount of time it takes to do one single mathematical operation. So it's measured now in gigahertz. That means one addition or one multiplication takes something on the order of a nanosecond to do. That number has not changed for a decade. So even though people say that computers are getting faster, they're actually not getting faster, they're getting bigger. You're doing more of these kinds of operations in parallel, but the actual operation speed has never changed. So what that means is that you can solve bigger problems in the same time. If you can solve a certain problem at a certain resolution, so if I get 8 times as much computing, I may be able to double the resolution of my model. But the model that I was solving, the amount of time it takes to solve it will not change. So that's what's called strong scaling. So what's in computing has happened is that weak scaling has allowed to happen, so you can increase resolution slowly, but you cannot actually solve problems any faster. And we need to solve problems in a given amount of time. So we need to be able to run 1,000-year simulations, and we have not actually cracked that problem. And this is, again, just showing as you increase resolution, I don't want to get into the detail. People talk about exascale computing and exaflop computing. Even at exaflop computing, what this slide is showing is that you will not be able to run a kilometer scale model of the whole Earth for thousands of years on any known computing technology today. What you can do instead is this. These chips are very, very good at doing the deep learning problem. So why is that so? So very simply put, the deep learning is you're trying to compute a transfer function between some set of inputs which are shown in red and blue. And let's say there's 5 and 4. So normally there would be like, you would expect a matrix of size 20 to connect all of these together. But if you put in a layer of neurons in the middle, you can vastly increase the number of mathematical computations you do to get from here to here. So you can make a very big parallel dense linear algebra problem. If you make multiple, deep learning means you have multiple layers of neuron. And the black lines, each one represents one mathematical operation. So you can see just to get from 5 inputs to 4 outputs, the number of mathematical operations in parallel you're putting in. So deep learning is something, dense linear algebra is something, it has high operational intensity, and models are very, very good at, the new chips are very, very good at doing these things. So people have used this, and so now we can start talking about weather and climate. So there's one class of problems which are called stationary, which means the external boundary conditions don't change. So emulation, which is teaching a neural net to mimic exactly what a physical model is doing. So that's what we are trying to do here. So this is taking what's called the Kuramoto-Sivashinsky equation, which is a well-known fourth-order nonlinear ODE that has chaotic properties. You run the model once using the actual model. You train on it using something called a recurrent neural network. And the training is pretty good in the sense that if you compute the difference between these two that's shown here, they remain, the green means that the difference is 0. So they remain very close to each other over many times, which are measured in this time unit, which is called the Lyapunov time. In a chaotic system, the Lyapunov time is the decorrelation time by which the chaotic solutions diverge from each other. So this solutions coheres for many, many 6 to 8 Lyapunov times, which means an extremely accurate emulation of a chaotic system. So it's able to do this, but the climate, on the other hand, is non-stationary. That means there are parameters which are in the model, which are external to the model, which are changing over time. In that case, this kind of model cannot capture it at all. And we have shown this using certain studies which I have marked here. So we can actually demonstrate this for climate models, that if the external boundary conditions change, so the climate becomes warmer. So a simple way of thinking about it is that if you train on 20th century climate as it is observed, you will not be able to correctly extrapolate that to 21st century because the temperatures have changed so much that in the training data there are no samples that correspond to what you'll see in the 21st century. And that you can demonstrate fairly clearly. So what we can do, though, is that you can maybe run very high-resolution models for short periods of time for future times and then use that for training. So that's one possible way of doing it. So this hierarchy of models, this ladder of models, we have to train one from the other. And a lot of the new interesting work is going on about this problem of using models of different levels of complexity and calibrating one against the other using machine learning. That's what we'll talk about. So again, some of these details maybe I'll skip. So this is a paper I wrote because there are some people who are saying general circulation models are obsolete. And this was a paper, arguing against that idea, showing that these models that people are proposing, these cloud resolving models, they themselves have so much spread that is not actually reducing the uncertainty that we have in the climate. So this is a study comparing the diamond models, which is the resolved cloud models, versus the CMIP models where the clouds are parameterized. And these models, again, this is another study. So there are, I keep hitting the wrong button. So another study which is using these very high resolution 10 meter or so scale models called LES models. And what they have done here is that they've taken a case where the CMIP models, the GCMs, don't agree amongst each other how they should be on a particular site. These numbers are particular sites around the globe where there are kinds of clouds that happen all the time, and they try to model them. And this number shows, the reds show quite a large spread between the models. And they've shown that if you take the same conditions but run the LES, run the large eddy simulation using those same conditions, you can actually reduce that spread. So it's a very compelling case that the LES can be used for training, even though you cannot use the GCMs. The LES can be used for training a parameterization that can span all the cases that we're trying to see. So how do we do this? So I'll make a sales pitch for what I'm calling model calibration using machine learning. So people talk about seamless models, which means the same model is used for both weather and climate problems. Whether you're trying to solve for 1 week or 2 weeks or 1 month or 10 years, you solve the same model. So it's called the forecast horizon. But even those models, they're usually calibrated differently because you can run higher resolution for shorter time. So you might take the same model, run it at higher resolution when you want to run 1 week. But if you want to run 1,000 years, you will reduce the resolution of the model. You always have something you're trying to optimize the model to do. So there is a cost function, or a loss function, as it's sometimes called. And then you declare it suitable. The models, we know that they do not converge cleanly with resolution. So because there's this parameterization, the equation that we've written for how an ensemble of clouds behaves, when you reduce the resolution, it does not, the parameterizations don't work very cleanly. So that kind of, if it were going cleanly, we call those parameterizations scale aware. So they're aware of the resolution of the model, and as you keep changing the resolution, their behavior changes in a way that's consistent with physics. That does not go away. Computation, I hope I've convinced you, is not going to make the problem go away. Some people still say all we need is a bigger computer. I don't believe that's true. There's lots of new observations. There's lots of fantastic satellite observations. In the ocean, there are these floats called Argo, which have started around 2000, which they float around, but they also periodically they sink and they take vertical profiles in the ocean. So for the first time since 2000, we actually know by observation the 3D state of the ocean. That has been a phenomenal advance in ocean forecasting. So if you assimilate this 3D data, you're getting the quality of the forecast has improved. So in ocean forecasting, ocean prediction, there is a pre-Argo and a post-Argo era. They're just so different. The quality of data is so dramatically different that the people who work with Argo data do not want to even look behind that. So what I'm arguing that with the wealth of data that we have, and all these other problems I'm mentioning, so what I'm arguing that we should do is to create a traceable hierarchy of models. So each one is a simpler model. It may be able to run for a longer time horizon, but it is physically consistent with a model, what I call up the ladder. So on Charney's ladder, you should be able to trace that entire sequence of models up and down the hierarchy using machine learning. So that's really what we're trying to do. So what does calibration mean? So it means that you take a certain number of parameters in the model, which are allowed to vary because they're not fully constrained by observations. You write some distance function between some variable in the model and what the same variable observed. And you write a cost function, which is the sum of all these. You normalize them, and you add some weights to them, and you write a cost function for it. You say that the parameters can be varied between some range, that you cannot randomly vary them to any value. I mean, you try not to do known unphysical things, which are called fudge factors here. It's not something we used to do that in the past. So there's a whole literature on what we call flux adjustments. When Manabe and Bryan first built their ocean atmosphere model, they could not get the fluxes to be zero. So there was an imbalance in the fluxes. So in order to get the model to run stably without gaining or losing energy, but conserving energy, they had to actually artificially adjust the fluxes. So it used to be called flux. It was one of the dirty little secrets of climate modeling. We've gone away from that. We don't need to do that anymore. So what observations you choose to write your cost function around, all that is dependent. Each lab decides what it wants to do. Two things we must keep in mind. One is that you cannot tune a particular metric. That is, you cannot use a particular metric in your cost function and then later claim success for that model because it does that correctly. So that's an overlap problem, or a data leakage problem, as it's called. The other problem is overfitting or overtuning. So the observed climate sequence, since it's a chaotic system, has a lot of variability, which is just chaotic. It has no particular reason. So if you ran the same sequence again, you will get a slightly different array. So you should not overtune either. So we talked about some of these things. And we do make these choices in our model. So this is an example from the GFTL model. So this is one, it's a kind of known bias in a lot of models, which is the clouds around the coast of South America. There is a cloud bias in the sense that in the model clouds, we are producing not enough clouds there, so that we create a warm bias in the southern hemisphere, which is what is seen here. So you can choose one of two things. You can choose to either, in your cost function, you can say, I want to minimize the error against the global cloud field, or I want to minimize the error just over the cloud field over South America, and you will get two different results. What happens is that what they showed is that if you reduce the error, if you put only the local error into your cost function, you will get a solution where the global error actually goes very high. So you cannot have both at the same time, so they had to make a choice. So these are the kind of choices. This is why the paper that we wrote about it is called The Art and Science of Model Tuning. There's a lot of choices that we make which might be aesthetic or based on preferences and so forth. So there's a lot of art that goes into it. So this is just, these are just papers for people who are interested. I'm not going to mention them. And you have also certain choices you make, like this is the 20th century temperature sequence, global mean surface temperature. The black and gray are the observed ones. The model that we published in GFTL in 2013 had what's called a cold bias. The latter half of the 20th century, it was cold by a few degrees. In this paper, what Golas et al. Showed is that by just changing one parameter or two parameters in the model, they can make the model either go colder or warmer. So if somebody said, you need to get the 20th century temperature correct, they could have actually tuned the model to do that. But if they did that, there would be other factors in the model which would have an error. So the cost function becomes a very key element in deciding what to do with these things. So there's been two groups of people who are trying to take these ideas of calibration and formalize the way we build these climate models. So not just do tuning by like trying things and then using your experience and your judgment to decide, making aesthetic judgments about the model. So one project which I work with in France is called HiTune. So it comes from the word that you use high resolution models to do the tuning. So you can write the equations, as I said, with the dynamical term which is resolved, and then a bunch of physics with a bunch of unknown parameters which are represented by lambda. You can write a function which is called the implausibility function, which says for a particular values of parameters lambda, is it plausible? Given the data, are these values of data plausible? It is just measuring the implausibility. And if the implausibility is below a threshold, then you cannot rule out these parameter values. But anything, if it's above the threshold, you say those are ruled out. You're left with a space inside the parameter space, which we call NROI, not ruled out yet. So we're not exactly doing an optimization problem. We're doing the opposite. We are just eliminating all the parameters which are not consistent with the data, which are implausible. And then you're left with a very small space, and then you can do this in repeated sequences, and so the NROI space shrinks for one metric, then you apply a second metric and shrink it further, and you can shrink it down until you're left with a very small parameter space that you have to evaluate using real models. And that's what they do here in this study. They're using these LES models as a reference, and they're taking a parameterization, and then they're trying to make the parameterization match the observed LES results. And they can do that fairly accurately. And so the way it's done, for example, these are three parameters in the model. It doesn't matter what they are. And you see this space is showing that all the values that are shown in gray are not plausible. They're not consistent with the data. So you've narrowed it down to a small set of values of DZ and evap. So this is a three-dimensional space. I'm only showing how it cuts through it. It's the only way we can demonstrate it. But basically, you can reduce the amount of parameter space we have to explore. And sometimes what can happen, this is what this is showing. So the same model running with two different resolutions. Sometimes the space called NROI goes down to 0. That means, what does that mean? It means there's no values of parameters in your physical representation which are consistent with the data. If there's no values, that means your equations are wrong. So that's what we call structural error. That means you have to go back to the drawing board and come up with a different physical representation of the system. So this system is not optimization. It is eliminating implausible values, and it is finding structural error. These are just some papers. A slightly related approach is followed by the group at Caltech, which is building the system called CLIMA, Caltech, and MIT. And they call this calibrate, emulate, sample. And again, I don't want to go into the details, but they applied it to a certain set of schemes for the boundary layer and shallow cloud parameterizations. Again, they calibrate, they're kind of finding the shape of the attractor where the solution might lie using some runs of an expensive forward model. So in both of these, what are you trying to do? You cannot explore the whole parameter space using a GCM because, as I said, the GCM is expensive to run. You're using emulators to explore the parameter space, finding some good values of parameters, and then only are you running the GCM. So this is a different approach to the same. Again, these are just some papers on this result. And one thing that we try to do, again, I'm skipping slides here to get to this, for example. So if you have an atmospheric ocean GCM, now you have a couple system. you have two components. So all the studies that have shown high tune and CLIMA and so forth, they've done this calibration of single components, just the clouds in the model. But you have to put it into a coupled system. Now, let's say you have an atmosphere and an ocean. The ocean, as I said, has many slow processes. The atmosphere has the decorrelation time is much shorter, so it moves faster. And you have unknown parameters in both sides. And you have to tune them both now in a coupled system. So when you do that, what happens? So you can test that using a very simple model with a lot of people, including Pedram, use extensively for studying. So it's called the Lorentz 96 model. It's a model with two time scales. So you have a set of nonlinear, it's a set of nonlinear coupled equations. The x's you can consider to be the slow variables, and the y's you can consider to be the fast variables. So in this case, the y is the atmosphere and the x is the ocean. They're coupled with each other. That is, the y's influence the x's and the x's influence the y's. So there's a coupling as well. And you can vary the strength of the coupling. How much does the atmosphere see the ocean and so forth. So what you do is you run the model, and it has these four parameters, f, h, c, and b. You run them once with a certain set of values, and then you go back and then assume that you don't know those parameters, and you try to find them using this tuning method. And what we have shown is that you can sometimes get into these kinds of states where, seeing here, for example, you have two values of the parameter which are both equally consistent with the data. This happens a lot when we're tuning coupled systems in reality. It's called compensating errors. You can tune two systems both to an erroneous state so that the joint coupled system gives you the right answer. So we can demonstrate using a simple system that this kind of compensating error situation can happen. Once that happens, when you have two possible solutions, and the way you recognize that is this space which I call NROI is not a single compact space, but it's kind of distributed. If it's distributed, that means there's different solutions that are both consistent with the results. And so we have to then try to use physical intuition or something to eliminate one of those solutions and pick the other. So that's what we are showing how it is done. What else can you do with machine learning? So this would be the another kind of really ultimate goal, which is to actually write down the solution not in the form of a neural net, but actually write it down in the form of an equation. How do you do that? You can start. So there's a paper by Zana and Bolton, who's also part of one of the one of the projects that Schmidt Futures has funded. So this is showing the same kind of turbulence problem in the ocean I showed you earlier. So the blue curve is what you might call the truth. So it's the model running at very high resolution. If you run the same model at low resolution, this is kinetic energy. The equilibrates to a very, very low value of kinetic energy. So you're not resolving all the turbulence. You're not getting enough energy in the system. So you get a very low level of energy. So you can use neural nets and try to find the difference between, you run the same model at two resolutions, you take the difference field and apply a neural net to find out what that field is, and then you can learn it. So that can be done. So that's a clear demonstration that simple deep learning works. What they tried to do instead, they wanted to actually find a closed form expression for the solution. So how do you do that? You write a symbolic expression for the right, which is kind of randomized. And you use neural nets to tune that expression further and further by adding more terms, subtracting more terms. So you can start with a random term, and then you can use, for example, genetic programming, which is like saying that if you write two random equations and the first one is closer to the solution, you eliminate the second one, and you take the first one and you make a random perturbation, add an extra term to that, and then you keep tuning it until you get a good answer. And they did a pretty good job. They didn't get as good as the neural net, but they got pretty close to, they got much closer than the unresolved one. And what was interesting is that the yellow and red curves, one of them is found by a neural net, and the other one is found by actually theoreticians working on the problem. So they were able to learn what's called a momentum closure almost as well as theoreticians did. So that's what this paper is showing. So these are all different ways in which you can take a hierarchy of models, whether it's by resolution and or complexity, and you can use neural networks to actually kind of get the links between those. And this is going to be important, and then non-local parameterization is another thing. I mentioned the fact that the physics is non-local. Neural nets don't really care whether the physics is, you can give them any vector of data and they will try to find a relationship. So if you can give it, you just have to make a longer vector. So instead of getting 1 column's worth of data, you can give it 9 columns worth of data. It's a bigger training problem. But if it's computationally tractable, it will find a relationship. And they've shown in this paper that non-local parameterizations actually do work. And of course, you can go non-local in time, which means you can capture the memory in the system. You can do various approaches as well. And the data wave project mentioned here is the one that Pedram is working on with colleagues in other parts of the world. So these are some papers on this subject. And I want to get to a final example of emulators, which is how they're used actually in policy. And here, they're not yet using machine learning and fields like that. I think they ought to, but here's what they're doing. So here is the problem. So the question that IPCC wants to know. So IPCC is the Intergovernmental Panel on Climate Change. It's the one that's trying to make information to policy based on what we learned from climate models. So they want to know the contribution to present-day warming coming from different forcing agents. So CO2 is only one of them, as you know. Methane is a forcing agent, and nitrous oxide. There are different things. And they all have a different contribution. If you're using GCMs to actually figure out how much each of these is contributing, how would you do this? You would take you would run one simulation with all the anthropogenic forcings turned on. So that's your baseline. That's the gray one. And many models will do this, so you will get this one is run with real models, the gray one. Then you would have to run one where CO2 is allowed to change, but everything else is kept fixed. So then you'll say, then you can attribute saying, this amount of warming came only from CO2 because I held everything else fixed. Then you'd have to do the same thing again for methane, again for N2. So they want to do this attribution for about 15 different agents. So if you imagine that each of these is you're going to start around 1850 and end in around 2100, that's typically what you do. You start from pre-industrial conditions and take it out to the end of this century. You would have to run these 250-year simulations for 15 different forcing agents. So that's adding up to a lot of years of simulation. So actually, we're not able to do this with models. So how did IPCC do it? They did this using emulators. So what they did was they took the existing climate models, and they looked at the spread, and you can see that they have a fairly wide spread. In fact, in the IPCC AR6, there's a lot of models that turned in very warm. But what they found is that the very warm models don't really capture the late 20th century temperature very well, so they kind of weighted some, and then they made a smaller set of models. And then using these models, which are extremely simple. They're not actual models. I call them models, but they're not like GCMs at all. They're simply fitting global mean surface temperature to a set of forcing agents like CO2 and so forth. And using that, they're able to just use these very simple models, which are not based on physics, and try to compute these relationships. So they call these emulators. So there's a whole literature on emulators, or they're also called reduced complexity models. And they vary a lot in design. So some of them are kind of they're like the single column models of Manabe. So it's like a GCM, but it's only one column. But there's some which are very basic models, which are called impulse response models, where you just make a change in the forcing and see how the system responds. Their advantage is that they're extremely fast. They're much, much faster than Earth system models by a lot, by millions of times. So you can run thousands, millions of cases. You can try any parameter combination you want. You can try all kinds of things. So currently, the connection to climate physics is tenuous because they're just trained on global mean surface temperature data directly. But what people are arguing for is that to use the Earth system model as a target for emulation. That means use machine learning, use that as a target, and actually try to learn the behavior of these emulators from the models. And the models also, as you can see, there are many examples of these reduced complexity models, and they don't all give the same response either. They're very different in design, and they give different answers. So there is what we call structural uncertainty across these. Only 2 of these, which are called FAIR and MAGIC, have been used by IPCC. The rest have not been used. Finally, I want to get to paleoclimate. So this is something that I think everybody should keep in mind. So there have been past episodes. This is 0 represents what present-day mean temperature looks like. In the past, it's been very warm. There's been an episode, for example, 55 million years ago called the PETM, the Paleocene-Eocene thermal maximum. So that's a very warm. It was like 14 degrees warmer than today. Then there's a slow period of cooling for many, so the scale is changing. So we are talking about hundreds of millions of years, then tens, then single millions of years, then we're getting down to thousands of years. So you get this long, steady cooling that runs over 50 million years. Then around 1 million years ago, you get into this ice age phase where you have these Milankovitch cycles where the temperature fluctuates in a fairly periodic way. The period has changed. There's been a 100,000 year period and a 40,000 year period. So people have theories about where these periods emerge from, but they're basically related to the orbital dynamics, the tilt of the ocean, the Earth's axis shifting in time. And what that means, during that time, what that means is that the ice comes and goes. So the ice sheets extend towards the equator in cold phases during the ice ages, and then they recede. So we've had these fluctuations, and humans can go back. So hominids at least can go back at least a million years. So I think Homo erectus is somewhere around here. So they lived in these periods, but they were basically nomadic. They follow the ice sheets and so forth. Then we get to what's called the LGM here, the last glacial maximum. And then after that, there's a warming. So it looks like the resolution has changed. So it looks like we're again on the upswing of an ice age cycle. Then around 10,000 years ago, this very interesting thing happens, which we call the Holocene optimum, where the temperature suddenly stabilized. And all of human civilization is built on these 10,000 years. If you can imagine, without this, agriculture is not possible, settlements are not possible. The stable Holocene climate is what is needed necessary. And then you look at the temperature spike since the Industrial Revolution. That you can barely see it. It's the very end of this curve. You can see what's happening. It's really compressed into the last few millimeters of this curve. So there's not much data for all this period. So machine learning requires a lot of data. The volume of data required is very high. So the paleoclimate cannot be used for training, but I would argue that it's a very, very good, what is called out-of-sample test for machine learning. So it's something that the data has not been trained on. So, and if you get a good model, then you should be able to represent some of these physics. Right now, I have to tell you models, even real GCMs don't do a great job. So this is for the Paleocene-Eocene thermal maximum I mentioned. These are a few observations. And you can see that the temperature is pretty warm near the poles, 17 here. And so it's the equator to pole temperature gradient is not very high. We know that that's true because we can find fossils of cold-blooded animals, alligators, and palm trees and so forth near the poles. So we know that it was really warm back then. But most of the models we run today are still showing the background colors are from models. The few squares are actual data. So the models are not in agreement with data. So actual GCMs have failed what I'm calling the out-of-sample test. But I'm still proposing it as a challenge. That's why we need to understand past warm climates in order to understand the future climate. So I'm going to end here. I hope I've not gone too far over time. So climate and weather, I'm going to predict, are going to start diverging in the machine learning era. Weather is a stationary problem, so you have enough data. So I'm going to make a bet here that within 10 years, the weather forecast you get on your phone or whatever device, implant, whatever you're carrying around 10 years from now, will be getting your weather forecast from machine learning, not by running an actual model, not by running a physical model. That's my bet. And there's many papers showing Pangu weather, GraphCast, and all that. They're getting pretty good. And some people are saying that maybe at this point, we should just dispense with theory altogether. We don't need it. Theory is for old humans. We don't need them. So there's a big op-ed in The Guardian. Are we witnessing the dawn of post-theory science? Point I'd like to always keep saying, computers are not getting faster. They're only getting bigger, which is okay for weak scaling problem, but not for strong scaling. But so that's another reason why I think weather is going to be easily done, but climate is going to need hundreds of simulations, hundreds of years in length. All models are optimized. Whatever resolution you go to, you're still optimizing the model to do something. But I think we are starting to see that we can do emulation quick. We have come up with techniques that seem to be very promising in terms of being able to do emulation. So you can take very high resolution models. You cannot run them for a long time, but you can learn to emulate them. And if you can emulate them, can you do calibration in weeks instead of years? Right now, the process of building and calibrating a climate model in a big lab like GFTL takes many years. Can we shorten that time? Remember always that everything cannot be trained on real observations because we need a lot of counterfactuals. If I showed you all these single force neutrons, what would happen if there's only methane was changing and nothing else? There's no observation for that. Can only be done by a model. Right now, these reduced complexity models do not have any relationship with climate models. I think we need to couple them. And just as the way we're using cloud resolving models or large eddy simulation models to train GCMs, we should use the GCMs to train the emulators that are used for policy. So these are some papers that I've been writing on the subject on Charney's ladder and whether GCMs are obsolete or not. We've been organizing workshops on this subject, which is where actually Pedram and I first met when we had a Princeton workshop on the subject in 2016. So this is my final slide. So there are many kinds of models. So these are these global cloud resolving models. There are local cloud resolving models. And then you have these paleoclimate models. You have all these these emulator models. The thing that links all of them is the GCM. And I think we can use machine learning to link all these models together. So that's my pitch. Climate modeling is taking us from the era of simulation to emulation. So I'll stop here. Thank you. Yeah, no.
Yeah. So what we use climate models for most is really that image in the bottom right, or really wanting to know what would happen as we push up and down each of those levers in the future. How well do we understand what features that the model need to get right and are most sensitive or most responsive to getting those levers accurate?
Yeah, I don't think we know that yet because at this point they're decoupled. But one thing that this feature selection and feature detection is one of the things that machine learning actually does well. So I think that's, again, one more argument for using machine learning to actually make the link, to make the emulators build on the features of the model that are most relevant for the problem, is what I would argue. I don't think we know the answer to your question yet. Which features are most responsible? Yeah. I think it's being recorded, so people should use a mic if possible.
I can ask a question. So you mentioned non-locality of the physics throughout the talk, but you know better than me, single column architecture is sort of imposed by the design of the GCMs, the localization and other things. And even this still limits us when we use machine learning techniques that can be non-local, like convolutional neural networks, like neural operators. Do you think this problem would go away, or we still have to manage to deal with the single column architecture? Like you mentioned, you showed some of the results from the MIT group that they can use a stencil, right? But for the gravity base, we need thousands of kilometers in the locality.
Yeah, but nothing is stopping you from taking data from anywhere and using it in your input vector. The only thing is that I would not violate physics to the extent of what Einstein, for example, said. You cannot have spooky action at a distance. So you shouldn't go to and say there's a point extremely far away which somehow influences this. But broadening the non-local stencil, I think you can broaden it as much as you want. I mean, as long as it's physical, that is within the time frame of influence that it's actually possible to have such an influence. I think it's okay. In fact, I hope you will try to go further because we know that the gravity wave spectrum, we can measure we know the cone. And you should be able to tell how much stencil you need, what stencil you need.
Yeah, I see that some of the GCM architectures, at least for the physics part, they don't like cross CPU interaction. But yeah, so that would be an issue.
Yeah, there will be one computational problem as well, which is that these are parallel models. So if you go very far away, then the data that you need may be on a different processor. So you have to use MPI or something to communicate the data. So that will be a technical issue that you will have to deal with. But in theory, you should be able to use the entire globe. You should be able to say, if you want to make your entire globe influence what is happening in your column, theoretically, there are computational limits, but I don't think there are theoretical limits on that. Yeah.
Any other questions?
Yeah.
So my question is more about the like when I think about the machine learning model being applied to one of these problems, you could evaluate in terms of the average error, right? And then, but this doesn't tell you much about the extremes. So I feel like the theoretical models would be more useful when you have extreme cases, and the machine learning model would be better when you have sort of like the usual case. And is there a way to sort of like combine this in a smart way such that?
Yeah.
Is there any mode that you're familiar with?
Yeah, I think, Pedram and I were talking about this at lunch. So models, even when you train on these kind of models with a turbulent cascade, machine learning does have what we call spectral bias. That is, it tends to learn the large scales first and the small scales later. And in fact, what we are really concerned about is what is happening at the small scales. That's where the extreme events are taking place and so forth. So don't have a clear answer yet, but what we can do is to write cost functions that actually remove that bias, that actually weight you towards paying more attention to the small scales rather than the large scales. So you can change your loss function so that you actually give, so two ways you can think about it. So you can use the mean, let's say you're training on precipitation. You can use the mean precipitation as your metric, or you can use the 95th percentile of precipitation or the 99th percentile of precipitation. All of them are equal. Computationally, they're all the same. But the 99th percentile will give you more accuracy on the tails of the distribution. Perhaps you will lose some accuracy of the mean. So there's going to be some trade-off there. So, but you should be able to, if you detect spectral bias, you should be able to try to tune your loss function to correct for it. Yeah.
Hi, our models are as good as our data, and these GCMs are trained on this, like the good GCMs are trained on LES models. So should we focus our energy on making LES models better so that our data gets better rather than working more on GCMs?
Yeah, models are not just as good as data. I would like to differ with that. Models also are based on theory. So we also have the laws of physics. So you don't have to, so we have Newton's laws, we have the laws of thermodynamics. They're all written into the model equations. Yes, they're based on data, of course. Everything is based on data. I agree with you. But you don't have to observe every single thing to know that momentum is conserved. So the Navier-Stokes equation imply momentum conservation. So some of it is baked into the equations themselves. And then on top of that, yes, we should make the LES models better. There's some disagreement between every level of model has structural uncertainty. So there's some disagreement between the LES models. They're not none of them can be taken as literally as a perfect model. But we can at least do as well as the LES models. And so in that sense, I think you're captured, because the LES models are, you can say they're simpler in the sense that they're making fewer assumptions about unresolved scales. They're basically saying that all you need is a turbulence closure. Everything else is resolved by the model. But the fact is, in reality, there is a difference between different LES models because of the numerics and choices of numerics and choices of certain things. So there are different closure schemes. So you can try to narrow those differences, and people are trying to do that. They're trying to devise tests for LES models so that you can converge them towards a particular kind of behavior. So you can do that.
Very interesting talk.
Thank you.
Your answer in all the modeling you did here practically was predicting change in temperature. Are you trying to do more than that when you say in fact the title of the talk is climate change? It's a much more complicated thing to be able to predict, and you can only do it in pieces, I guess.
Yeah, yeah. So yes, you're absolutely right. We are trying to predict a multivariate function which has many components to it. So we definitely want to measure temperature and precipitation, but we also have in the models ecosystems in them. So we're trying to model the future of ecosystems as well. So we're trying to model a very large number of things. So the number of different outputs you get out of a climate model is quite large, and if you include the 3D states, if you want to improve this, stratospheric temperatures are varying differently from tropospheric temperatures. We're trying to model all of that. So roughly, the models are, again, I think needed because, so again, just going back to an example, you can tell a machine learning to only you can only put temperature into its cost function. It'll get temperature right, but it might give you complete nonsense for humidity, let's say. A physical model won't do that because the physical model has an equation that tells you the relationship between temperature and humidity. It's a covariance between these two, so it cannot violate that. The only way a neural net will not violate that is we actually tell it to use the covariance in the cost function. If you don't give it the covariance in the cost function, it will allow temperature and humidity to vary independently of each other. So that's another reason why the models actually, even for the people who are doing weather, they're actually training on model output, because that's the only way they can get physically consistent data to train on. So your point is well taken. We are not just doing temperature. We're trying to do a whole host of things, but they're all connected with each other in a way that we hope that the equations describe correctly.
Well, if you do it well, you'll be able to predict hurricanes, right?
Yeah. Yeah.
Any other question?
Hi, Mr. Balaji. I'd be remiss if I didn't ask. I think you kind of just hit on it, but what do you think might end up missing from model-less weather in this post-data science that you mentioned?
I'm sorry, I didn't quite catch the question.
What do you think might end up being missed in machine learning models of weather if that is exclusively what ends up being on our weather app, for example?
Yeah. So in a very broad sense, we think the system may have some thresholds. Like when a number exceeds some value, it will flip into a different state. So if we know that, for example, the Lorentz system has these two states that it keeps oscillating between these two different states. Or you can think of them as tipping points. So there are tipping points in the system which will cause it to suddenly go into a different state. If you only train on data in one state of the system, if the system has metastability or bistability, it has two possible stable states to be in. If you only train on one, it doesn't capture behavior in the other. So people have tried to deal with this when they know the different stable states of the system by actually trying to make sure that it captures both. But this is the kind of thing which I expect I think when they fail, they will fail spectacularly. They will not just be slightly wrong. They will completely miss something that happened altogether. I mean, so for certain problems, this is very high stakes. Even for weather, it's very high stakes. I mean, missing a major forecast, like a major extreme event, missing a forecast is a big deal. Even now for weather centers, they are, because lots of money is at stake if you miss a forecast of a hurricane making landfall versus not making landfall. So these things are going to be very critical. So when I say that 10 years from now, I think it'll happen, I will take some of these considerations like what you're raising into account. So I think if Google is going to say, I'm going to run my own weather forecast, I think they will be very careful to run lots of these scenarios of what would happen if they missed Hurricane Harvey. What would be the consequence of that? They would have to think carefully about that before taking this on. I agree.
Okay, great. So we have a reception outside, and please join us. But first, let's thank Balaji for this fantastic presentation.
Thank you for that.